Hello dear friends, welcome to this lecture of the Riemann integral. In this lecture, we will study some properties of Riemann integral. We know earlier these properties as properties of definite integral, but we shall prove these properties using the definition of Riemann integral in terms of upper sum and lower sum. So, I have written a property here. So, we are going to study these property, that is f is Riemann integrable over the closed bounded interval a to b, where and c is a point between a and b. Then f is Riemann integrable over the closed bounded interval a to c, also the closed bounded interval c to b, and integration a to b of f is equal to integration a to c of f plus integral c to b of f. So, this property first we shall prove, and then we shall prove the property that if lambda is a constant, then integral a to b of lambda f is lambda times integral a to b of f, where lambda is a constant. So, this property also we shall prove in this lecture. So, first we shall see the proof of this theorem number 3. The statement of theorem 3 is f is Riemann integrable over the closed bounded interval a to b, and c is a intermediate point in the interval a to b. Then function f is Riemann integrable over the closed interval a to c, also the closed interval c to b, and we have to prove this result, that is integral a to b of f can be split in two parts, integral a to c of f plus integral c to b of f. First we shall see, consider this, let f is Riemann integrable over the interval a to b. Suppose f is Riemann integrable on the closed bounded interval a to b. Then by definition or the existence theorem, when we say f is Riemann integrable over this closed bounded interval a to b, the set of points of interval a to b, the set of points E of interval a to b where the function f is not continuous is of measure 0. Then, or before we can write that, then f is continuous by existence theorem. F is continuous at almost every point in the interval a to b, and therefore the set E, of points of the closed interval a b where f is not continuous or at which f is not continuous is of measure 0. That is the meaning of the property holds almost every point. Where the property does not hold, the set is of measure 0. So, f is not continuous is of measure 0. Then see, if you consider this interval, now C is a point between a to b. A is less than C is less than B. Therefore, then see, this is the interval a to b, and C is a point in between this, any point. And if the set of points of a b where f is not continuous is of measure 0, we can consider the intersection of this with the interval a to c. Then the set E intersection a to c is also of measure 0. So, what is the meaning of this? There are some countable number of points of discontinuity of the function in the interval a to b, and therefore, if we restrict that set to only this interval, then certainly there will be a countable number of points in the interval a to c where the function is not continuous. The property holds for a to b, and therefore, the same property will hold E intersection a to c, the interval means this interval. and that set is also of measure 0. Similarly, and therefore what this implies, the function f is Riemann integrable over the closed interval a to c. Therefore f is Riemann integrable over the closed interval a to c. And exactly similar way we can consider E intersection of the interval c to b, closed interval c to b. Then that set is also of measure 0, and therefore the function is Riemann integrable over the interval closed bounded interval c to b. Similarly, we can say f is Riemann integrable over the closed bounded interval c to b. So thus we have proved here that if f is Riemann integrable over whole interval a to b, then f is Riemann integrable over the interval a to c and also the interval c to b. Now we have to prove the property, this property or this result, that is integral a to b of f is equal to integral a to c of f plus integral c to b of f. Now what we shall consider is the subdivision of this interval a to b, and that we will be considered in terms of the subdivision of a to c and then subdivision of the interval c to b. Now we shall denote the subdivision of interval a to c by sigma, and we shall denote the subinterval of the subdivision of the interval c to b by tau. So suppose this is sigma, and suppose this subdivision can be considered as say tau, and now we can write as let sigma be a subdivision of the interval a to c, and tau be a subdivision of the closed interval c to b. Then the subdivision of the whole interval a to b will be sigma union tau. Then sigma union tau will be subdivision of the interval a to b. Is a subdivision of the closed bounded interval a to b. Now what we should consider is the lower sum, and now the lower sum of f on sigma plus the lower sum of f on tau, the subinterval tau. See, lower sum of f on sigma, this interval a to c, and the lower sum of f on this interval c to b, and the subdivision is tau. So lower sum is on of f on sigma plus lower sum of f on tau will be equal to the lower sum of f on sigma union tau, and this lower sum is, now we know the lower sum is less than or equal to the lower integral. So this is less than or equal to the lower integral a to b of f, because the least upper bound or maximum value of the lower sum is the lower integral, and therefore this is any value, and any value will be either less or equal to the lower integral. Now what we have, that is this sum is less than or equal to the lower integral, and therefore so lower sum of f on sigma plus lower sum of f on tau is less than or equal to, and this is the lower integral, but f is Riemann integrable, and by definition of Riemann integrable function, the lower integral is equal to upper integral is equal to the integral, and therefore we can write this integral simply as integral a to b of f, since the reason is since f is Riemann integrable. So since f is Riemann integrable over the closed interval a b, the lower integral of f is equal to the integral a to b of f. Lower integral is equal to upper integral, and that is equal to the integral of the function. So thus we have this result. And now what we shall do is we take the least upper bound on this subdivision sigma first, keeping tau fixed. Now taking LUB of the left side, taking LUB on the LHS and keeping tau fixed. For a moment we will keep tau fixed, and then we will next step we shall take the LUB of this subdivision tau, keeping epsilon fixed. So one by one we are taking the LUB on these subdivisions. So first we shall take the LUB of on the left side, LUB on the left side, LUB on subdivision sigma. So LUB on the subdivision sigma. So keeping tau fixed on the left side on the LHS, we get, now see, I shall write this as LUB on sigma, L lower sum of F on sigma plus, now we are keeping this second term as it is, lower sum of F on tau, and this is less than or equal to the integral a to b of F. This remains fixed because F is Riemann integrable and lower integral is equal to the integral. And what is this lower integral of this LUB of lower sum of F on sigma? By definition, this is the lower integral, and sigma is the subdivision from a to c, and therefore this is lower integral from a to c of F plus lower sum of F on tau, and is less than or equal to integral a to b F. This is by definition. But you see, this is a lower integral of F from a to c, but F is Riemann integrable from a to c, and therefore the lower integral is same as the integral from a to c, and thus this can be written as, that is, integral a to c of F plus lower sum of F on tau is less than or equal to integral a to b of F. The reason for this can be written as, since F is Riemann integrable, since F is Riemann integrable over the closed interval a to c, and therefore integral a to c of F is same as integral a to c F. Lower integral is equal to the integral, and thus now this is the result we have. Similarly, now what we take the LUB on this subdivision tau, we get, now this will change, subdivision tau is from C to B, and so we can further write as, similarly taking LUB on subdivision tau, we get, now see, this is the integral from c to b, that is this first integral will be as it is, integral a to c of F, plus the second on taking the LUB on tau. See, this will be LUB of L of F over tau, that is the lower integral from c to b. But lower integral from c to b is same as integral from c to b, because F is Riemann integrable from c to b, and therefore we will get integral c to b of F is equal to, or is less than or equal to, the right side is less than or equal to integral a to b of F, and we suppose this result as 1. Now what we should consider is, as earlier, taking the subdivisions sigma and tau, the original subdivision sigma and tau, now we write the result in terms of upper sum. So this result we have written in terms of lower sum, now we write the same result in terms of upper sum. Now taking Now taking the original subdivision sigma and tau as in the earlier case, taking original subdivisions sigma and tau, we have see, I shall write the same result in terms of upper sum of f on sigma plus upper sum of f on tau, and that is same as upper sum of f on sigma union tau, and but this upper sum will be greater than or equal to upper integral, that is the change. So this is greater than or equal to the upper integral of f a to b, so it is the upper integral. And because we know the GLB of upper sum is the upper integral, smallest value, and this general value, and therefore this will be greater than or equal to the upper integral, and thus this result will be upper sum of f on sigma plus upper sum of f on tau, and this is greater than or equal to the integral from a to b of f, because this upper integral is equal to the integral, because f is Riemann integrable, and thus we get this one. And so now what we should consider is taking the GLB of this, taking for we have defined the upper integral in terms of GLB of upper sum, lower integral in terms of LUB of lower sum. So for upper sum we have to take the GLB, greatest lower bound, least upper bound and greatest lower bound, short form for this, taking GLB on the subdivision sigma, keeping tau fixed as in the earlier case, we get taking GLB on the subdivision sigma and tau, we will write the result directly, taking GLB on the subdivisions sigma and tau successively, we get as in the earlier case. Now if you, what will happen if you take the GLB of this, GLB of upper sum over sigma will be the upper integral from a to c, and that we should get as the upper integral from a to c plus, and GLB of upper sum from this subdivision tau will be the upper integral from c to b, but the upper integral and the lower integral for these intervals are the same, because these are Riemann integrable, and therefore we are directly writing integral a to c of f plus integral c to b of f, and that is greater than or equal to integral a to b of f, and we suppose this as second. Now see the first and second. So the left side is less than or equal to the right side, and this says that the left side is greater than or equal to the right side. That means these two must be the same, then and only one, then 1 and 2 holds together. So from 1 and 2 we get the equality. So from 1 and 2 we get the result. We get the integral a to b of f is equal to integral a to c of f plus integral c to b of f, and thus this proves the result. So that means we can divide the intervals in any part. The result can be extended, not only 2 intervals but 3 and n intervals. So that will be integral a to c, then c to any other interval, then that point to next point, etc. That the whole interval can be covered like this. So this proves the result. This proves the theorem. So thus we have proved theorem number 3, and so this proves the theorem. Now we shall state the theorem number 4. If f is Riemann integrable function over the interval a to b, and lambda is any real number, then lambda times f is Riemann integrable over the closed bounded interval a b, and integral a to b of lambda times f is equal to lambda times integral a to b of f. So this result we know earlier, That means if there is a constant multiplied to a function, then we can write the constant outside the integral. Lambda is a constant, real number means it is a constant. So if you have integral a to b for a definite integral, or we can consider the intervals like this 1 to 3 and 5 times f, then we can write this as 5 times integral 1 to 3 of f. So that is the meaning of this result. So we have been using these results earlier also, but we shall prove this with the help of definition of Riemann integral in terms of the upper and lower sum. Now first thing is we have to prove this lambda times f is Riemann integrable on the closed bounded interval a to b. Now we see if lambda is 0, then the result is very obvious, the theorem is obvious, because if lambda is 0, this becomes 0, integration of 0 is 0, and 0 into this integral is again 0, so two sides becomes equal and there is nothing to prove. If lambda is 0, then the theorem is obvious. That is obviously true. Now what we should assume first is lambda positive. Suppose lambda is greater than 0, and now first we should show this result, that if f is Riemann integrable, then lambda f is also Riemann integrable. If, or we can write directly that lambda f is continuous wherever f is continuous in the closed interval a to b. Now we have lambda f is continuous, lambda is constant, lambda f is continuous wherever lambda f is continuous wherever f is continuous. In the interval a to b. So how this is so? Because f is continuous in the closed bounded interval a to b, and lambda is a constant function, or lambda is constant means lambda is constant function, and that is also continuous. So product of two continuous function is continuous. So lambda f is continuous wherever when f is continuous, then lambda f also becomes continuous, and this shows that lambda f is Riemann integrable over the closed bounded interval a to b, and thus lambda f is Riemann integrable over the interval a to b. So that is the first part. Now what we should consider is the next, that lambda is greater than 0, and we will consider the maximum value of function f. Let j be an interval of ab. Let j be any interval in a to b, then maximum value of the function over this interval j, or we can consider maximum value of the function lambda f. Now there are two functions, lambda f and f. So first we have shown lambda f is also Riemann integrable. Now we should consider the maximum value of lambda f over the interval j, and that will be equal to lambda times maximum value of f on the interval or over the interval j. Now it is easy to verify since lambda is greater than 0. Now how this is so? If you consider f as the function which takes some discrete values. So suppose f is a function having values, or so for example we are considering this say 1, 4, 5, 7, any values can be taken, and what is the maximum of this, maximum of f, and the interval may be taken as 1 to 7, and so maximum value of f on this interval j will be, the interval is 1 to 7, over the interval j is maximum value is 7. Now if you consider 5 times f, or say 3 times f, so what will be 3 times f? we have to multiply each number by 3, and this becomes 3, 12, 15, 21. And what is the maximum value of lambda f, or that is 3f? Lambda is taken here as 3, and maximum value of 3f over j will be, this is 21, and 21 is same as 3 into 7. That is this is equal to 3 into maximum value of f over the interval j, which is 7. So that this is easy to understand, and that we have, because this is possible because lambda is positive. So it is a constant, and that we can consider lambda into maximum value of the function f over j. And in terms of maximum value, we define the upper sum. Therefore, the upper sum of lambda f on this any subdivision sigma, or we should consider, let sigma be a subdivision of the interval a to b. Let any subdivision of the interval a b, then, or therefore, upper sum of lambda f on sigma will be equal to lambda times upper sum of f on sigma. By this result it follows, because we know we have defined upper sum in terms of maximum value multiplied by length of the interval, sum of these products. And thus now we can consider the GLB on both sides, and therefore this implies taking GLB on both sides, or we can write this as a GLB of upper sum of lambda f over sigma is equal to, lambda is constant, it will remain the same. We have to take the GLB on this upper sum, GLB of upper sum of f on sigma. And what is this? The integral a to b of lambda f. By definition, GLB of upper sum of lambda f on sigma is the integral a to b lambda f, or that is actually the upper integral. But because lambda f is Riemann integrable, upper integral, lower integral and the integral are all equal, and therefore we are writing simply the integral here. It is upper, but it is the integral a to b, and of lambda f is equal to lambda times, and similarly what is this? This is the integral of f over the interval a to b. It is f, upper sum of f, and again f is Riemann integrable, so upper integral of f is same as the integral of f, and here the lambda is greater than 0, and we assume this result as 1. Now we have proved the result for lambda greater than 0, but the result must be proved for any real number, non-zero. For 0 it is obvious. We have proved the result for lambda greater than 0. Now we shall prove the result for lambda less than 0, and for that purpose we can assume mu, another constant which is negative. Second part we will consider as, let mu is greater than 0. See second part. Suppose, or let mu less than 0, then we will consider lambda as negative of mu. Then lambda, if you take as negative of mu, mu is negative, and negative of negative will be positive, then lambda will be greater than 0. Now we will consider the maximum value of negative f on j, and what will be that value in terms of minimum value. So we have to use this result further for this second part. Now again I will write the same function earlier we have written, that is f is. So f is say having some points, discrete values, what we have written 1, 3, 5, 7, like this. So what is the maximum value of f? Maximum value of f is 7. And if I consider negative f, then what will be the negative values? -1, -3, -5, -7. And you see what is here minimum of f. Minimum of f is -7, this value. And therefore the relation is maximum f is equal to negative of see, this value is 7, maximum of negative f. So we should consider the maximum value of this, maximum of and minimum value of this we should write. So I shall consider maximum of minus f. So what will be maximum of minus f? Maximum of value of this, maximum value will be negative 1, because the values are having negative sign, and minus 7 will be the smallest value and this will be the greatest value. So maximum of minus f is minus 1. And you see this value here in terms of f here it is minimum. So here we have minimum of f is 1, and therefore maximum of minus 1 is minus minimum of f. See this. When we write f in terms of these values, negative f will be having negative signs, and therefore minimum of this is 1 and maximum of minus f is minus 1, and therefore maximum of minus f is negative of minimum of f, and thus this result we are writing. If you write the minus sign outside, then we have to take the minimum value. Minimum value of this is because of the change in sign, minimum of f over the interval j, and therefore if you take the upper sum of this, therefore upper sum of minus f on any subdivision sigma will be minus, and small m means the lower sum we have defined in terms of small value, minimum function, minimum value of the function, and therefore this will be L of lower sum of f on sigma subdivision, and thus this is the relation that we have to note. Upper sum of minus f is equal to negative of lower sum of f, and now we will take the subdivision here, and thus, or we now consider the integral a to b of negative f. Now integral a to b of minus f will be in terms of this upper sum, that is GLB of minus f upper sum, GLB of upper sum of minus f on sigma, and again we have written this is equal to minus L of that is the lower sum of this we have to consider, that is GLB of this is minus L lower sum of f on sigma. And now when we consider this negative sign outside here, that will be minus of this GLB becomes LUB, minus LUB of the lower sum, LUB of lower sum of f on sigma. See, this is the same as like earlier. When we take the negative sign outside, this GLB becomes LUB, and here you see if you take this negative sign outside, this maximum value becomes minimum value. So like this, or you can refer again the function, say f is equal to, f is 1 3 5 7 we have written, and what is the negative f? Negative f is minus 1 minus 3 minus 5 minus 7, and we have the what is the GLB of this negative f. So GLB of minus f, this is greatest lower bound is minus minimum value, that is minus 7, and what is the LUB of this? Least upper bound means maximum value of f, maximum value of f is 7, and therefore you see GLB of negative f is equal to, see, LUB, that is a negative of LUB of f, and this minus 7 can be written as negative sign LUB of f, that is minus 7 is LUB. So if you take negative sign outside, this GLB becomes LUB. Please note this in these results for negative values, and thus we have this is negative of LUB of lower sum of f on sigma, and that is minus, what is the LUB of lower sum? That is lower integral on sigma. Sigma is the whole subdivision of a to b that we have considered, and therefore it is integral. Actually this is lower integral, but lower integral is same as the upper integral because the function is Riemann integrable. All are equal, upper integral, lower integral, and that is the integral only. So this is integral a to b f, and thus we have the result as integral a to b of negative f is equal to negative integral a to b of f. That means this minus sign can be written outside the integral, and that result we should assume as the second result, integral a to b minus f is equal to this. So we write it as second. Now we should consider integral a to b of mu f. Mu is negative. So now integral a to b, or you can consider next part as next, integral a to b mu of f is equal to integral a to b. What we have assumed here is lambda is negative mu, and therefore mu will be negative of lambda and negative lambda of f. Yes, mu is negative, and then lambda is negative mu will be greater than 0, that is positive. Lambda will be positive, negative or negative, and lambda is positive, but this negative sign we can write by the second result outside of the integral, and that I shall write negative integral a to b of lambda f. So this is by 2, using 2 here, and further this I can write negative, and lambda f I can write lambda times integral a to b of f. This is by 1, and finally you see what is minus lambda, that is minus lambda is mu, and therefore this becomes mu times integral a to b f, or thus we have proved that is integral a to b mu f is equal to mu times integral a to b f, and where mu is less than 0, and thus this proves that this result is true for constant is negative. Mu is a constant in terms of lambda, lambda is also a constant. So we have proved here the earlier result, that is integral a to b lambda times f is equal to lambda into integral a to b f when lambda is greater than 0, and here we have proved the same form of the result when mu is less than 0. So this proves that this proves integral a to b of lambda f is equal to lambda times integral a to b of f for any real number lambda, positive or negative it may be, and this completes the proof. So we have proved the theorem 4. So thus today we have studied two properties of Riemann integral as theorem number 3 and 4. So thank you for watching this lecture.